Welcome to the lesson on the fundamentals of robotics. Upon completing this lesson, learners will be able to identify various robotic components and describe degrees of freedom and types of joints associated with them. Learners will also be able to classify robots based on joint types and power supply and name some of the commonly used robots in EV manufacturing. In EV manufacturing, robots play a critical role in ensuring precision, efficiency, and consistency throughout the production process. Let us look at the four main components of a robot. They are the power source, controller, manipulator, and end effector, as illustrated in the images. We will discuss more about these components in the upcoming slides. Firstly, let's look at the power source. The power source provides energy to drive the robot. Here, we will focus on two primary power sources, electric and pneumatic. The power supply drives various robot functions, including motion, manipulation, and interaction with the environment. Sensors gather information about the surroundings, enabling the robot to perform tasks effectively. Alternatively, pneumatic systems powered by air compressors drive grippers or suction tools, with regulators, filters, and lubricators ensuring precise operation in assembly processes. Let's discuss how electric energy powers the robots. Typically, 6 main components constitute the robot's power unit. First is the main power unit, which converts AC power to either a different form of AC power or DC power. This unit receives power from the wall or floor and transforms it into a usable format for the system. Next, we have a control panel, a basic interface that enables power on-off control, an emergency stop button for malfunctions, and the ability to switch on certain robot functions. This panel serves as the primary user interface for the power supply aside from the main on-off switch. Following this are circuit breakers and safety relays, depicted as numbers 3 and 4 in the image. These components, along with the user interface, provide automated safety measures. They automatically cut off power to protect the system during surges, malfunctions, or other unforeseen events. Maintenance personnel must reset these components manually. Number 5 highlights the programmable logic controller, abbreviated as PLC, which may vary depending on the system. This controller connects to the network and drives the robot, making decisions based on programmed logic. It allows for implementing if-then rules to execute tasks with specific instructions. Finally, terminal strips, marked as number 6, facilitate troubleshooting and provide quick access to various electrical components within the power supply. Now, let's look at the pneumatic power supply, which utilizes pressurized air to transfer force. These systems can be used to operate control grippers, actuate suction cup grippers by applying vacuum or negative pressure, and perform blowing off applications for surface cleaning or applying finishes with pressurized materials. Additionally, pneumatic power can drive cylinders, like hydraulic cylinders. Let's look at the main components of a pneumatic system. The image shows 3 key components: air tank, regulator, filter, lubricator, referred to as RFL, and air compressor. First, we have the air tank, which stores pressurized air. This tank provides the necessary air supply for demanding applications. Second is the RFL system, which is responsible for air control. It consists of 3 elements: the regulator, the filter, and the lubricator. The regulator reduces the pressure from the air tank to the required level for the specific application. The filter removes particulates or treats the air to ensure its suitability for the end application, especially for mechanical parts like grippers, where it prevents damage and malfunctions. The lubricator treats the air with lubricants, which is beneficial for moving parts that require lubrication during operation. The third component is the air compressor, which replenishes the air tank and builds up the pressure used for the intended application. The compressor can be powered by electricity or gas. These 3 components, along with tubes or pneumatic lines that connect to the end application, comprise the essential elements of a pneumatic system. The controller is the second main component of our system. Robot controllers execute programmable instructions to manage motion while utilizing control algorithms that continuously monitor feedback data like position, speed, and force to ensure the robot achieves precise movements and positioning during operation. The controller, often referred to as the brain of the robot, processes feedback signals from sensors and actuators. It then sends actuation signals to drive the robot's joints, which might involve controlling motor power, joint velocity, or end effector motion. The controller is responsible for programming the robot to perform specific tasks. For example, if the robot needs to move from point A to point B, the controller handles all the intermediate steps. The operator might provide high-level instructions, such as going to this point, picking up a part, moving to another point, placing the part, and then going to another point to pick up a third part. The controller then translates these instructions into precise movements, ensuring the robot completes the task efficiently and safely. The complexity of the controller varies depending on the robot's type and the required tasks. This image displays a control pendant, which houses the controller and provides a user interface. This pendant allows operators to input instructions, interact with the controller, and deploy automated tasks when needed. This image displays the back of a control pendant, and while specific features may vary, certain elements are typically present. One crucial component is the dead man switch. When the operator releases this switch, the robot immediately stops functioning. Power is cut off, and the robot remains stationary. Another element, visible on the front of the pendant, is the e-stop button. This serves a similar safety purpose. If the operator notices an error or problem, they can press the e-stop to immediately shut down the robot and prevent further damage. Additional features of the control pendant may include a user interface, a universal serial bus, commonly known as a USB port for connecting to a computer and uploading pre-programmed control programs, and controls for directly manipulating individual joints and robot values. The interface is typically designed to be user-friendly and intuitive, often with a plug-and-play approach. Let's look at a high-level overview of the control aspects of the robot. The controller is a computer within the control pendant that governs the robot's actions and executes various tasks. The image shows an Arduino board as an example controller. This integrates several key components: a central processing unit with memory and program data, input-output modules, and connections to actuators like motors and speakers. Control systems can implement various algorithms including on-off, open-loop, closed-loop, and feed-forward control. On-off control manages simple reciprocating motions, open-loop operates without environmental feedback, closed-loop utilizes sensor feedback for task completion, and feed-forward anticipates system responses. Robot control pendants typically use closed-loop control algorithms because they require feedback from sensors such as position encoders, force sensors, etc., to ensure accurate and precise movement of the robot's joints and end effector. In industrial applications, this control architecture is implemented through more robust systems like programmable logic controllers, or PLCs, which use ladder logic to define actions based on specific conditions. Other systems include distributed control systems, known as DCS, and supervisory control and data acquisition, known as SCADA systems. Each of these systems offers different levels of control and monitoring capabilities. The entire system connects to a programming device, shown as a laptop in the illustration, for configuration and monitoring. Now we will look at the manipulator and the robot arm itself. A robot's arm or manipulator serves as its mechanical body, comprising members and links that execute physical movements according to instructions received from the control pendant. Its design determines motion capabilities across 1 to 7 axes, with movement limitations defined by its configuration. Regular maintenance is essential for optimal performance, and the choice of construction materials can be adapted based on specific operating environments, such as hazardous conditions. A critical aspect of robot operation is the home position system, which serves as the zero-position reference point for maintenance, recalibration, and safe storage. Each robot's joints are equipped with specific indicator marks consisting of paired notches and lines. When these markers align perfectly, they signal that the joint is in its correct home position. This simple but effective visual indicator system allows operators to quickly verify proper positioning. For example, when a notch and line pair are properly aligned, as seen in typical maintenance diagrams, this confirms the joint is at home position. Conversely, any misalignment between the notch and line pair indicates that the joint has deviated from its home position. This visual confirmation system is essential for ensuring accurate robot positioning and safe operation during various maintenance and operational procedures. Let's look at the degrees of freedom, abbreviated as DOF, a concept that was mentioned earlier. DOF refers to the number of independent variables that define a robot's state. Generally, in practice, there are 6 fundamental DOF. 3 translational, and 3 rotational. Translational DOF encompasses movement along 3 axes, left and right, forward and backward, and up and down. Rotational DOF involve rotation around 3 axes. Think of the movement like that of an airplane. Roll is the rotation around the longitudinal axis, like rolling left or right. Pitch is the rotation around the lateral axis, like ascending or descending, with the nose pointing higher or lower than the tail. Yaw is the rotation around the vertical axis, like turning the plane left or right while maintaining its altitude. Robots achieve various motions by activating joints corresponding to these DOF. For example, a prismatic joint, which translates linearly, allows for forward and backward movement of the end effector. Similarly, rotating joints enable rotational DOF. When discussing robots, the terms degrees of freedom and axes of control are often used interchangeably. However, axes of control specifically refer to the number of individual joints or actuators the robot possesses. For example, a robot with 5 joints, 3 rotational and 2 prismatic, has 5 axes of control. While this typically implies 5 DOFs, there can be exceptions. A robot with 6 DOF or 6 axes of control along its arm, when mounted on a moving platform like a mobile base, gains an additional DOF, resulting in 7 total axes of control. This provides redundancy and enhances the robot's capabilities. Let's look at the types of motion associated with these DOFs. As discussed, there are 6 fundamental DOFs, 3 translational and 3 rotational. These directly translate into the types of motion that robots can execute. The 2 primary types of motion are translational and rotational. Translational motion involves linear sliding movement between 2 linkages facilitated by a prismatic or translating joint, also known as a slider. Rotational motion involves circular movement between 2 connected linkages. In this case, one linkage remains fixed in space while the other rotates relative to it. Rotational motion is one of the earliest observed types of motion and remains highly prevalent in robotics and robotic construction. Robot manipulators utilize 5 standard joint types that define their degrees of freedom by restricting one or more of the 6 standard DOFs. These joints are categorized into 2 motion types, translational or prismatic, and rotational, also known as revolute. The linear joint, known as the L joint, allows straight-line movement like a robot arm extending outward on a linear track. The orthogonal joint, or the O joint, enables perpendicular translational motion, similar to a sliding drawer mechanism. The rotational joint, known as the R joint, permits circular movement around a fixed axis, much like an elbow joint rotating in a fixed plane. The twisting joint, or T joint, facilitates rotational motion along its own axis, comparable to a screwdriver turning motion. Finally, the revolving joint, known as V joint, allows for sweeping rotational movement, functioning like a robot arm swinging in an arc around its base. The table summarizes the number and types of joints for each robot type. These factors significantly influence the robot's performance and capabilities. Let's look at some examples of how these joint types can be combined. The images illustrate the robot itself and its workspace envelope. It's important to remember that different robot configurations create unique workspaces and interaction capabilities with the environment. Articulated, or RR, this robot has 3 revolute joints, resulting in a work envelope resembling a donut shape. Cartesian, or PPP. This robot utilizes 3 prismatic joints, leading to a rectangular work envelope. Cylindrical, RPP, or similar. This robot typically includes 1 revolute joint and 2 prismatic joints, resulting in a cylindrical work end envelope. The specific joint configuration may differ depending on the robot's construction. Spherical. This robot typically has 2 revolute joints and 1 prismatic joint. This configuration allows for 2 rotational DOFs and 1 translational DOF. The spherical robot and the articulated robot exhibit visually similar work envelopes. However, they differ in the orientations that their end effectors can achieve at a given point. Scara. This robot has a distinctive semi-cylindrical work envelope and is well suited for various tasks. When selecting a robot for a specific application, such as part placement, manipulation, painting, or welding, it is essential to consider the robot's workspace and work envelope to ensure it can effectively perform the required tasks. So far, we've discussed the power supply, the controller, and the robot's mechanical components responsible for movement within the work area. Now, let's focus on the end effector, which is essentially a tool head or gripper that enables the robot to interact with and manipulate its environment. In EV production, specialized end effectors are used for tasks such as precisely welding battery packs, applying paint finishes to car bodies, and assembling intricate electronic components. The selection of appropriate end effectors is essential for ensuring the quality and efficiency of EV manufacturing processes. There are two main types of attachments used with end effectors: grippers and tools. Both are designed to perform specific tasks and are typically replaceable or detachable, allowing a single robot to perform multiple tasks within the same workspace. The first type of end effector attachment is the gripper. As the name suggests, grippers are used to grab, hold, and manipulate materials. Gripper movements can be classified as either prehensile or non-prehensile. Prehensile movements, like human grasping, require a thumb-like action for tasks that involve grasping objects and manipulating them with precision. Examples of prehensile motions include palmar, cylindrical, spherical, lateral, and oppositional grasps. Non-prehensile movements, on the other hand, do not require a thumb-like action. These include hooking and spreading motions, where the object is grasped from the inside or by spreading fingers to secure it. Other types of grippers include suction cups, as previously mentioned, and magnetic grippers for handling magnetic materials. The second category of end effector attachments is tools. These tools are typically designed for highly specific tasks. For example, a drill bit is a specialized tool used for drilling. Tools can be classified into different categories, such as specialized material applications and machining and assembly. In specialized classification, welding tools are specifically designed for welding operations, cutting tools for cutting materials, and 3D printing tools are used in 3D printing processes. Material application includes tools for handling materials, such as paint nozzles for applying paint to car parts. Tools used in machining and assembly processes include drill bits, screwdrivers, and riveters. Industrial robots in EV manufacturing are specialized machines designed for specific assembly and production tasks. Let us look at some of the commonly used robots in EV manufacturing. The spot welding robot, equipped with a welding gun and effector, employs rotational and revolving joints with 6 degrees of freedom to precisely join metal panels and components. For battery assembly, a dedicated robot using linear and orthogonal joints with 4/6 DOF handles the delicate task of placing and connecting battery cells using gripper or suction end effectors. The paint-spraying robot achieves uniform coating application through a combination of rotational and twisting joints, utilizing 5/6 DOF with a spray nozzle attachment. For heavy-duty tasks, the material handling robot combines linear and revolving joints in a 4 DOF configuration, using magnetic or vacuum grippers to move substantial components throughout the manufacturing process. Specialized robots handle the finishing and quality assurance aspects of EV manufacturing. The wire harness robot employs rotational and orthogonal joints with 6 DOF, using a multi-tool head to precisely route and connect electrical systems throughout the vehicle. For quality control, the quality inspection robot operates with linear and twisting joints in a 3/4 DOF configuration, utilizing advanced vision systems and scanners to detect potential defects in the assembly. The windshield installation robot combines linear and revolving joints with 5 DOF to carefully maneuver and place large glass components, employing a suction array end effector to ensure secure installation of these delicate materials. In summary, robots are comprised of 4 essential components that work together as an integrated system. The power source, which can be either electric or pneumatic, provides the necessary energy for operation. The arm or manipulator contains mechanical linkages that follow the principle of 6 standard degrees of freedom, though these are typically constrained in specific patterns to achieve desired motion types. The controller acts as the brain of the system, making decisions about the robot's movements and operations. Finally, the end effector serves as the specialized tool that varies based on the specific task to be performed, completing the robot's functional capability. Thank you.